Okay, this is our last topic in 2.2. We're going to look at absolute value inequalities. And as the title suggests, we're going to have inequalities that include absolute values. How do we handle those? Well, there are two ways that the situation or the inequality could end up. There could be an absolute value less than some number. In this case, what we would be saying is that the distance between whatever's in the absolute value, I've just written an x here, and 0 is less than a. That's what this is saying. So remember, the absolute value of x represented the distance between that value and 0. So here, that distance between x and 0 is less than a. That means x can take on values all the way from negative a up to a, not including, of course. And that's represented by this compound inequality, negative a, strictly less than x, strictly less than a. That's an and type inequality. Okay. Right, so that's an and type inequality, and this also works for any other inequality symbols. So if you like less than or equal to, that would also work for this one. Okay, so I mean the strict. So this is strict, but also the non-strict inequality would also be okay here. So that would change these as well. Okay, if the inequality is pointing the other direction, so the distance between x and 0 is greater than a, as with this one, we get an or type inequality. That means x could be a value that's larger than a, the absolute value would then be larger than a, or the value of x could be less than negative a, in which case the absolute value of that would then be greater than a. So that gives us this compound inequality with the or. X is greater than a or x is less than a. Also works for the non-strict case as well. Okay, so let's go ahead and take a look at an example, a few examples actually. We'll start with this first one. 4 plus absolute value of 3 minus 2y less than or equal to 6. Okay. The first thing we need to do is to get the absolute value by itself on one side of the inequality. We can see that's not the case here. We've got a 4. We need to move that over. So we'll subtract the 4, and we get absolute value of 3 minus 2y is less than or equal to 2. Okay, now this has the absolute value less than or equal to 2. Less than or equal would be this type, so we've got the compound inequality. So we can write that immediately. Negative 2 less than or equal to 3 minus 2y less than or equal to 2. Okay, and now we can solve this. So we can subtract the 3. Get some more room here. So we have negative 5 less than or equal to negative 2y less than or equal to negative 1. And now we want to divide by negative 2, but to do that, we have to switch the inequalities. So we have 5 halves greater than or equal to y greater than or equal to 1 half. All right, and so that leads to a solution set of 1 half, comma, 5 halves, always smaller and larger. Right? So if we wrote this another way, it would be 1 half, well, 5 halves greater than or equal to y greater than or equal to 1 half. So y is between 1 half and 5 halves. So always put the smaller number first. Okay, and you could graph that on a number line as well. All right, let's look at the next one. So here we have negative 3, absolute value, 4 minus x is less than negative 6. First thing we want to do is to divide by negative 3, but to divide by negative 3 would be to isolate the absolute value. We're going to have to switch the inequality symbol. All right, so we have absolute value of 4 minus x greater than, and then we have negative 6 divided by negative 3, which is 2. Okay. Now we can continue here. This is this would be an or type inequality. However, we can stop here because you look at this absolute value. This number right here whatever this expression is, it's always positive. Okay? Actually, no, we can't, right? Because this could be positive, it could be less than 2. Right? So we cannot make any conclusions about that right now. Anyway, so we've got absolute value greater than A. So that's an OR type. So we'll have 4 minus x greater than 2, or 4 minus x less than negative 2. Right? And we'll solve both of these. Right? So we have opposite of x greater than negative 2. Switch the inequality, x is less than 2. From the first one. Or we'll subtract 4, so negative x less than negative 6. Divide by negative 1 or multiply by negative 1, x is greater than 6. Okay. And the conjunction is or here, so we're going to take the union of these two. So we've got negative infinity to 2, union 6 to infinity. Right, and again, you could graph that on a number line. All right, let's look at this last one here. Again, we need to divide by a negative number. That means we're going to switch the inequality symbol. So 4 minus t in absolute value is less than negative 3 divided by, or 6 divided by negative 3 is negative 2. And here we can, if we look at this inequality here, the absolute value is said to be less than a negative number. We know an absolute value can not be negative, right? It's always 0 or some positive number. Right? So we know right away this has no solution. You could, of course, this is a and type inequality. You could set this up, work it out. You would see that the intervals are disjoint. There's no overlap, and so this would not work. Okay, so here we have the absolute value inequalities. Absolute value less than a number, right, means an and type inequality. So you can just put the value and the absolute value between the number a and the opposite of a. If you have the absolute value greater than a number, that gives you an or type inequality. That means the absolute value, part in the absolute value, is either greater than a or less than the opposite of a. Okay, and that wraps up our discussion for linear inequalities in one variable.